Today we're going to talk about the multiplication principle. And so let's begin with a problem. An exam consists of two true or false questions along with a multiple choice question, with possible answers being A, B, or C. Determine the number of possible ways this test could be answered by a student. So we'll begin by drawing a happy tree here, and we have two choices for that first question, so we'll draw true or false corresponding to that first choice. And then for our second question, depending upon our first question, we have different breakdowns. So if you have true for the first question, you have a true or false option. If you have false for the first question, you have a true or false option. And then off of each of those, we have a multiple choice question. So we'll create another layer of branches. So if you had true and true for the first two questions, you could have A, B, C. If you had true and then false, you could have A, B, C. If you have false and true, you could have an A, B, C option. And if you chose a false and false, you could also have an A, B, C option. This creates a whole bunch of different scenarios. So for the first case, we had true, true A as one of the possible scenarios, then true, true B, and then true, true C. And then we could do a true, false A, true, false B, true, false C. And we can continue in this manner. We get the false, true A, false, true B, false, true C, false, false A, false, false B, and false, false C. And that's all possibilities, all possible outcomes that we have. And if you count them in total, we have 12 possible outcomes or possible ways to actually answer this test. Okay. This is kind of tedious, and what happens if we had, say, 20 multiple choice questions? This would be impossible to do. So we got to think of a better method. And one is, if we have 3 questions, we can label them question 1, question 2, and question 3. And then for the first choice, we had 2 options. Second one, we had 2 options. And the third one, we had 3 options. So now, if you multiply those 3 pieces together, notice you get 2 times 2 times 3, and you get equals 12. And so that's another way to come up with the answer. And maybe that leads us to a bigger sort of underlying principle. And in fact, it does. It's the multiplication principle. So if an event can be described as a sequence of k steps with n1 possibilities in the first step, n2 possibilities in the second step, and nk possibilities in the kth step, then we can find that total number of outcomes. And the way we do this, we'll draw some lines here. So we have a first, second, and so on and so forth. You could draw the third and fourth. We have all the way up to the kth step. And in the first possibility, we had n1. In the second possibility, we had n2. And all the way up to that k step, we had nk possibilities. So notice what happens. Before, if you think about the previous problem, we just multiplied these values. It went 2 times 2 times 3 equals 12. The same principle applies whether it's 3 steps, as in the 3 questions, or if it's k steps, as in this general principle. So it goes n1 times n2 times all the way up to nk. So you're just multiplying straight across depending upon the steps of the sequence. And notice that's a key component, steps of the sequence. So you can rewrite this as n1 times n2 dot dot dot, with that being multiplication all the way up to nk. So let's take a look at a problem here. A character consists of an uppercase letter, a lowercase letter, or a single digit, and we want to determine the number of 8-character passwords that exist. So there exists 62 characters in this, and you can find that by realizing that their uppercase letter has 26 possibilities, the lowercase letter has 26 possibilities, and the single digit has 10 possibilities. And we can use the addition principle to come up with our 62 different characters. So now we want to determine the number 8-character passwords. And so the way we can do this is actually list out the possibilities in terms of the different characters. So we'll fill in the blanks. We have a first character choice, and then a second character choice, a third character choice, a fourth character choice, a fifth character choice, a sixth character choice, a seventh character choice, and an 8th character choice. So notice each of these, it depends on what character you choose in that position. So it's a sequence of steps, essentially, meaning the multiplication principle. Keeping that in mind, well, our first position, we had 62 choices there, and then we had 62 choices for our second position. We had 62 choices for our third position, and we can continue in this manner, 62 for each of these slots for the possibilities. So this gives us 62 to the 8th, which is 218 trillion, 340 billion, 105 million, 584,896 passwords with 8 characters. And that might sound like a lot. I mean, that's a huge number. And when you think about it, it might be a large number, but computers can actually carry out these calculations. And as of today, there's a computer that can end up attempting 350 billion passwords every second. So that means if you just give it a little short amount of time, it can actually crack a password of this length. So how do we fix that problem? Well, the way we do it is we actually add in more and more character possibilities. And obviously, the more characters we have, the harder it is for them to be cracking the code. So let's take a look at our next problem. A character consists of an uppercase letter, lowercase letter, or single digits, just like before. But if a password consists of 8 to 10 characters, then how many different passwords exist? So now we have some different cases. You have an 8-character password, which we've already calculated. We can calculate the 9-character password. And we can start that off just in a similar manner to the 8-character password, right? We have 8 blanks to start with, and we already know what happens there. There's sequence of steps. And then we add in that 9th character position, and we're still applying the multiplication principle. So we just put in an extra slot of being 62. And so that means we have 62 to the 9th different 9-character passwords. And in a similar manner, we can actually carry out the 10-character password calculation. And so we just draw our 10 blanks, and once again, multiplication principle, because this is sequence of steps for creating our character, the first character, second character, so on and so forth. That's 62 to the 10th, 10-character passwords. Okay, so we have to think now, we have used the multiplication principle, but you don't have any crossover for a sequence. If I'm having an 8-character password, a 9-character password, and a 10-character password, those aren't sequence of steps at the same time. And what they are, they're separate situations, and we're just choosing one of those 8, 9, or 10-character passwords. So we can actually use the addition principle now. And we have the number of 8-character passwords, the number of 9-character passwords, and the number of 10-character passwords. We can actually draw a Venn diagram for this. They're all disjoint sets, because if you have an 8-character password, it's not a 9-character password. And in the 8-character password, we know there's 62 to the 8th possibilities. In the 9-character password, there's 62 to the 9th possibilities. And in the 10-character password, there's 62 to the 10th possibilities. So the number of passwords with 8 to 10 characters is just essentially our addition principle. We use and apply that here. 62 to the 8th plus 62 to the 9th plus 62 to the 10th. This gives us an improvement on the number of passwords. And it ends up being 853 quadrillion, 54 trillion, 792 billion, 520 million, 188,672 passwords. So a huge impact in terms of the number of passwords. And as we lengthen that number, it makes our actual password more and more secure.